So I'm starting with quite elementary material, quite something that everybody will be able to follow. But I do have the intention of moving it in a kind of research direction. So the immediate topic is these things called cyclic quotient surface singularities. And Hirzebruch-Young continued fractions. Okay, so quotient singularities means, this means a manifold divided by a finite group. But what I'm doing now is really much simpler, because this is just a cyclic group acting linearly. So these singularities are going to be called 1 over R of 1A. So this is notation which now everybody uses. This means the cyclic group mu R inside C star. So this is the group of order R. So you can think of this as being the group generated by x of 2 pi I over R, if you want. And then it's the group is isomorphic to Z mod R. Making an isomorphism involves choosing a particular generator. So if you're a topologist, you don't have any doubt that this is the best generator. Any primitive root of unity makes this group into Z mod R. And the rest of the notation here, this means that we have two-dimensional space, C2, which is, these are characters of the group mu R. So with the action x, y maps to epsilon times x and epsilon to the power of a times y, right, where epsilon is in mu R. So if you think about this notation, you don't actually need to choose a basis for this group. You don't need to choose a generator for this group. This notation makes perfectly good sense in its own right. So in this notation, this thing is the group that we're dividing by, the group mu R, and these are characters of the group. This is the every irreducible representation of this group is one, has dimension 1 and looks like some power of epsilon. So here, so R is usually greater than or equal to 2, integer, and A is co-prime to R. Usually, let's take 0 less than A less than R. Okay, so the picture I have in mind is here is C2, and it's mapping down to a quotient. So here is x, C2, divided by this mu R. And it's an orbit space, and it's also an algebraic variety. Right, so I'll say just a little bit more about what this means later. But anyway, this is a very kind of primitive, simple-minded construction. So let me say what the rest of this Hirzebruch-Young continued fractions are. And so, it's convenient just to do some kind of example. So for example, let me just take 7 over 3, which is a rational number, and I'm going to write a continued fraction. So I'm going to write this is 3, 2, 2, meaning this is 3 minus 1/2 and then minus 1/2. Okay, so I'll do slightly more complicated ones later, right? But I hope everybody can see what's happening here. 2 minus 1/2 is 3/2. 1 over 3/2 is 2/3. So 3 minus 2/3 is 9/3 minus 2/3, so that's 7/3. Right? And I'll explain later there's a reason for choosing minus signs here rather than plus signs. So in the standard theory of continued fractions, which goes back, I think, to the ancient Greeks, or ancient Egyptians or Babylonians, I don't know, anyway, has you write pluses here. But anyway, it's sort of a bit nicer to write minus, and I'm only going to minus. Okay? So the question is, we can ask this question: why is the orbit space an algebraic variety? So the thing I'm going to do is, so C2 with coordinates xy is spec of the ring C of x and y, and the group here, mu r, the cyclic group is acting on this variety, and so of course it's also acting on this. It's also acting on this ring. And I'm going to say x is, I'm going to take spec of the ring of invariance. So I take C of xy, and then here I write mu r. Right? So this thing here is spec of, mu of r. So ring of invariance. This is the same construction as in Galois theory. I've got a group here which is a group of automorphisms of this ring, and then I take the guys in the ring that are fixed under this, this action. Yes? So, of course, I'm going to explain what this spec is. But first of all, I'm going to explain what C of x, y, mu r. So this is the ring of invariance of mu r action. So how do we know there are any invariants? Well, the thing you notice immediately is that if I take x to the power of r or y to the power of r, these are invariants. Yeah, that's obvious. If I take x to the power of r, it's getting mapped to epsilon to the power of r times x to the r. Epsilon to the r is 1. Right? So can we see any more? Well, I can see one. I can see one by doing this. If I do x to the power of r minus a times y. Right. Well, when I do I take my epsilon, it gets x to the power of r minus a times x. Sorry, to the power of r minus a times epsilon to the power of a times y, and that cancels. Right. So this guy is invariant. right? And now I'm going to say, so there's a little lemma here that says an algorithm based on Hirzebruch-Young continued fractions gives all the invariants. So first of all, before saying exactly the answer to the question, let me sort of just stand back a little bit and say I want to do the following thing. So let me leave this to the side just for the moment, although the construction I'm giving is exactly explaining what this algorithm is. So this is a digression, but it's a completely relevant digression. So let M be Z2, sorry, isomorphic to Z2 be a lattice. So it's just an abelian group that happens to be isomorphic to 2 copies of Z. So the point here really is this is isomorphic to Z2, but I haven't yet chosen the basis. Right? So, and let sigma inside M, let me say MR, be a cone, a convex cone. Right, with the base spanned by, let's say, V0 and V primed. So here's my lattice, and here's some cone that I choose. So cone, it means it's a convex cone based at the origin, and I say, so let me not kind of, so here's V0 some vector, and here is V prime some other vector. Okay, and I'm just going to make two assumptions here. So I'm assuming that M is Z2, and I'm writing down these vectors. So I'm assuming here that V0 and V primed are primitive. Primitive means that they're not multiples in M. You can't divide them by anything in M. So if I start off at this point 0 and head off in that direction in MR, the V0 is the first lattice point I come to. Right? And I'm also assuming that they're linearly independent, so that they're linearly, so these are guys in M, and they're linearly independent over Q. Okay, so if you're very naive, you might say, well, automatically, this V0 and V primed are a basis of M. So, of course, they're a basis of M over Q. They're a basis of MQ. I think probably most people here have done first year linear algebra, so will know that means they're a basis of MQ as a vector space over Q. But of course, that the lattice could be bigger. Yeah? And so here I'm going to make a construction which looks like a geometric construction. So I'm going to take first the parallelogram V0 plus V primed. So this is the unit parallelogram. And so in here there are finitely many lattice points. So let's draw these lattice points, sort of something like this. Right? And now let's draw their convex hull. Okay, so this picture here is called Newton Polygon. Of M sigma, and you can see what it is. So the thing I've done here is I've taken all of the lattice points here which are in this cone, and except for the origin, I'm not looking at the origin, and then I'm taking the convex hull of these. So they're because I've got V primed and V naught, the only thing that's happening here is happening in this first quadrant, in this cone, in this unit cube of the cone, and there are only finitely many lattice points here. So I'm taking all the guys here, all the lattice points in this thing, and I'm taking the ones that are closest to the origin. Right? So the construction is draw the Newton polygon so convex hull of the points of M intersect sigma. So, not equal to 0. Right, so I call this line, there's a line there that goes from V primed, from V naught to V primed, and I call the points along the boundary V1, V2, V3, V, and so on, Vk minus 1. And this V primed is now Vk. Right, so V naught, V1, Vk minus 1, Vk equals V primed are the successive points on the Newton boundary. So this looks like a geometric construction, but I'll show you straight away that this is just determined in a completely automatic way by these Hirzebruchian continued fractions. Right, so then there's a kind of little theorem here. So for all v, for all I, so there's three statements here. For all I, for all I, if I take vi, vector vi and vector vi plus 1 is a basis, is a z basis of M. Statement 2, for all I, if I consider vi minus 1 vi plus 1, these are related by vi minus 1 plus vi plus 1 equals vi to the power of, in a minute the notation will turn from additive into multiplicative, but at the moment these are just points in a lattice. So AI vi for some AI greater than or equal to 2. 3. V1 equals 1 over R of V primed plus R minus A. Okay, let me not use, let me use different notation. V naught, where R over V equals A1, A2 to A k minus 1. Okay, in other words, I say, draw this picture. Imagine these guys here are vectors coming out of the origin. Right? Then there is a little rule for how to form Vi plus 1, knowing Vi and Vi minus 1. If you know this coefficient Ai, then you know how to jump from this basis here, from this basis of this cone, to this basis of this little subcone. Right? And if you do this several times, you go all the way from this first basis here to this last basis there, and you're doing something which is given by this continued fraction. So remember, this means here A1 minus 1 over, and then A2 A k minus 1. Yeah? So this is A1 minus 1 over A2 minus 1 over, and so on and so forth. So it's the same as this construction here. So the point here is that I'm working in a lattice M. The lattice is isomorphic to Z2, but I'm not making any preferred choice of basis here. There isn't any preferred choice of basis. So I make this construction, which is geometric. It's just convex hull of these points. So I take this is all the points. So there are infinitely many points, of course, in this front cone. I'm taking all of these points except the origin, and I'm taking the convex hull. Then I say, look along the boundary of this convex hull. You get this line, which is called the Newton boundary, right? And then the points on the Newton boundary are related like this, and then you can go back and say, oh yes, and the lattice itself is V naught, V1, Vk, sorry. So this is Z2 like this. Z2 generated by these two plus Z times V1. Yes? So these guys, the original V naught V primed, are not a basis of M over, not necessarily a basis of M over Q, if R is not 0, if R is not 1. Right? So let's... you know, I stated it's a theorem, but this is really very trivial. Right? So, first of all, why is it... come back to this. So the advantage of stating things as a theorem is that you just have to prove very, very trivial things. So here's the origin. Here's Vi. Here is Vi plus 1. Okay? So this is a little parallelogram in the plane. Okay, and what do I know? Well, there are no lattice points along there. So here, no points of M. So in the first instance, that's because the V0 here was the V0 was a primitive vector. From then on, it just follows by induction, right? So there are no lattice points along there, right? Also, there are no lattice points along there, right? There are no lattice points inside here. This is just by construction, because I chose this thing here to be the convex hull of all the lattice points. So all the lattice points must lie above that line, right? So no lattice points. Yeah, okay. There are no lattice points here, 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 and also there are no lattice points along here. That's because I said these are the successive points on the Newton boundary. So if there were a lattice point here, he'd be one of the VIs. Right? Also, there are none up here. None here. Right? Because there are none here because if I had V in M, then VI plus 1, VI plus 1 minus M minus V would be in M. Right? So if I had a lattice point here, then I could reflect him. I could do this, point out there and doing reflecting, take the same point down there, and that would now be in there. Right? And so therefore, this is this parallelogram is a fundamental domain for translation by M. Right? There are no lattice points in there, so if I just translate everywhere, I get every lattice point as the corner of some translate here. So therefore, i.e. VI plus 1 is the basis. Okay? And so, you know, the next statement too is also sort of more or less obvious, because, so, you know, here I've got VI minus 1, VI, and VI plus 1. So let me draw it like this. Okay, so by 1, so proof of, this was proof of 1. Proof of 2. Well, so by 1, VI minus 1, VI is a basis, and VI plus 1 is also a basis. And so let's take this guy VI plus 1. So this is certainly some point in the lattice, so certainly he's a linear combination of these two guys. So he's got to be of the form A times VI plus B times VI minus 1. Right, but then this B must be minus 1. And there's basically no choice about this, because you know, I want to be able to go back and make VI minus 1 as a linear combination of VI and VI plus 1. So now I must have determinant 1. There's a transformation here which is going from VI minus 1, VI into VI plus 1. And well, anyway, must have determinant. Well, let me start with determinant plus or minus 1, right? But it's got to be negative because when I make this change of coordinates from here to here, so these are really, as written, they're oriented bases, right? So there's also a basis, but it's actually an oriented basis. Right. So the point is really that this, if I do VI minus 1 to VI, maps to VI plus 1, is given by a matrix (0, 1, minus 1, AI). I'm sorry, BI, AI. Yeah. So this is just saying that VI, the second entry here, VI, is equal to the first entry here, VI, and the first entry here is equal to this combination. Sorry, this combination here of these two vectors. Right. So it's given by VI plus 1 equals A VI minus VI minus 1 plus AI VI equals 0 times VI minus 1 plus VI. Right, that's just this change of coordinates. So finally, part 3. So calculate VK, this is V primed, as a function of V0, V1. Right, and so, basically I'm taking a product of these matrices. So I have absolutely no idea how to write down the product of matrices in the right order. But if you do, let me do a numerical example so we can understand what's happening later. But anyway, if I do 0, 1, minus 1, A1, 0, 1, minus 1, A2, 0, 1, minus 1, A K minus 1, right, this is a change, this is K minus 1 changes the bases going around here. So it's change of basis from this basis to this basis to this basis to this basis. Right, this thing here turns out to be minus, I think it's Q primed over minus P primed, minus Q over minus, plus Q and plus P, where P over Q is, where P over Q is A1, A K minus 1, and P primed over Q primed is A1, A K minus 2. So, just think about how you multiply these things. I'm not going to explain this. I'm just going to do it in a numerical example. This is sort of, if you try to set up the notation here in a systematic and sort of rigorous way, it becomes basically poisonous. So all of this is written in several papers that I can refer to. So I want to do an example, and I want to do something a little bit bigger than that 1/7 of 322. So let me look at the one I've prepared. So I want to think about this quotient group action, C2, divided by 1/19 of 1/8. And I say that the invariant monomials are, so they're guys of the form x to the power of I, y to the power of j, where I, j are in integers, and I plus a j, this is 1 over r of 1a, 1 plus aj is divisible by r. So this is a set of numbers I comma j. So this ij belong to a lattice M. Yeah. So let me just think about this case. So I'm going to draw a Newton polygon, and I'm going to draw it like this. So here I write y to the power of 19. So I know that y to the 19 is invariant. And here I write x to the power of 19. Okay, now I said earlier, I know one other invariant guy. So I know that x to the power of 11 times y to the 8, times y is invariant. Right? Because if you think of the character of this group that acts on it, it's 11 times the character plus 8 times the character, so it's 0. Right? So here I'm supposed to write down x to the 11th. Now where is x to the 11th? Somewhere in the middle here. This is x to the 11th. X to the power of 11th y. Okay, and I know that this must be a point on the Newton boundary because this exponent y is the smallest possible exponent. It's y to the power of 1. So there can't be any points intermediate here. Right, so this is the beginning of my Newton boundary. And now what do I have to do? Well, what I have to do is write down 19 divided by 11. So can we do 19 divided by 11 as a continued fraction? Okay, so what's the ceiling of this number? What's the integer immediately above this number? Obviously it's 2. Yes? And then it's 2 minus a bit. 2 minus how much? 2 minus 3 over 11. So 3 over 11. Well, how do we deal with 3 over 11? We think of it as 11 over 3. Right? And this is 4 minus a bit, and the bit is this is 4 minus 1/3. Right, so this number here is 243. Yes, I hope everybody can do this calculation. And so if I do 2 minus 1 over 4 minus 1 over 3, I get 19 over 11. So that number 2 there is saying, if I take the next point on the Newton boundary, he'll be like this, where this thing here is an arithmetic progression, right? So in other words, this guy here has got to be x to the power of So this was, going from 19 down to 11 was minus 8. So I'm going to do minus 8 again. Right? And here it's going to be y squared. Right, and next I'm supposed to do this thing to the power of 4, this thing to the power of 4, minus this. Yes? So in other words, so what's this to the power of 4? It's x to the 12th, y to the 8th, divided by x to the 11th y. Right? And so this number here is x y to the 7th. Yeah? And so this is my 2, 4, and 3. Yeah? So this 19 over 11. When I took this number here, when I took this, this guy here, which is invariant, I had to take x to the 11th is x to the power of r minus a, y to the power of 1. Yes? And the fraction I'm working with is not r over a, it's r over this 11. Right? And so this number here is not this number, that's why I wrote it b in the previous, on the previous blackboard. This is x to the power of b times y. And the b is r minus a. Right? So if I continue going here, so if I did 2 here and I got over the end, then it would be because 19 over 11 is less than 2. 19 over 11 is bigger than 2, so I can afford to take one more step in that direction. Having taken one more step in that direction, I can't go any further because I'd be beating this 2. Right? And so I get here. And so I have to say, what multiple of this guy do I need to take so that he's bigger than this? Yeah? So I'm taking this monomial here to the power of 4 and then dividing by that. And then that manages to stay inside the cone. Okay? Is this clear? I mean, you see already I'm mixing, I'm thinking of this here as the point 19, 0, and I'm thinking of this as the point 11, 1, and so on. Right, and so there's a lattice here, a lattice of monomials, a lattice of invariant monomials. Okay, so this is supposed to explain the following thing. So this is the theorem again. So I'm looking at 1 over r of 1a. So this is the group action mu r acting on C2 by x, epsilon x, y, raised to epsilon a, y. The quotient is the ring of invariance is polynomial ring in V0, V1, V2, Vk, where V0 is x to the power of r, V1 is x to the power of r minus a y, and Vi minus 1, Vi plus 1 equals equals Vi to the power of ai where R over R minus A is A1, A2, A k minus 1. Okay, and the Vk is y to the power of R. Okay, so in other words, I start off with polynomial ring in two variables x, y, and a little group acting on it, a bit like a Galois group. A Galois group acting on a ring, and we know the ring of invariance. So it's generated by this V0, V1, Vk, and given by these formulas. And then the relations are, so you know, well, I already own a lot of relations here. I have Vi minus 1, Vi plus 1 equals Vi to the power of Ai. Right? And these AI come in a completely automatic and rather easy way just by knowing R and R minus A. So I can calculate huge examples of this just by guesswork. So, but on the other hand, we don't yet know all the relations. There are other relations plus other relations. So these are called long equations. Vi, Vj equals intermediate. Right. So this is sort of basically. Let me think about the example over there. So I had V0 is x to the 19th, V1 is x to the 11th y, V2 is x cubed y squared, V3 is xy to the 7th, and V4 is y to the 19th. Right? And, you know, just by construction, we see the equation V1 squared equals V0 V2. Right, I should write it the other way around. V0 V2 equals V1 squared, and V2 to the 4th equals the other way around. V1 V3 equals V2 to the 4th, and V2 V4 is V3 cubed. Right? I assert that there is also relations V0 V3 equals something, V1 V4 equals something, and V0 V4 equals something. So let's calculate what these are. Okay, so how much? So that can be deduced by syzygies. So you know, I mean, I'm not going to explain formally what this means. So how are we going to find a relation V0 V3? So, you know, I mean, one way would be to say, well, V0, for God's sake, V0 is this guy here, and V3 is this guy. Let's take the product, and let's find a way of writing him as a product of these intermediate guys. Yes? I don't know if that makes sense. take x to the 19th times x y to the 7th. That's x to the power of 20th, y to the power of 7. So he's somewhere in this cone. That product is somewhere in this cone spanned by these two guys. So he must be some combination of these two. So if you think about it, it's got to be this one squared times that one. All right? However, you can see this, you know, by sort of algebra rather than waving your hands and saying geometry. So let's do, to find V0, V3, let's do this. Let's take this equation, V0, V1, V3 equals V2 to the 4th, right? And let's put a V0 in front of this. V0 in front of that. Okay, so here I've got V0, V2 to the 4th, and I can substitute in this equation. So this is V0, V2 times V2 cubed, right? And the V0, V2 in turn is V1 squared. And I can cancel V1. So why am I allowed to cancel V1? Well, you know, this is everything here is taking place inside the polynomial ring. All of this is contained inside polynomial ring in x and y. Right? And polynomial ring in x and y is an integral domain. So if I've got an element, for example, x1, I've got this element v1 there, then he's not a zero divisor. You know? And so then this gives a relation, v0, v3 equals v1, v2 cubed. Right? So you can just write x0 to the 20th, y to the 7th. So he's this one times this one cubed. Yeah? Etc. So, you know, exercise, find v1, v4, and v0, v4. Okay, so right I is the ideal of relations between V0 up to Vk inside this polynomial ring. Inside polynomial ring C UV invariance. Right, so I've got a bunch of monomials in there. I know that they generate all invariant monomials. I want to find all the relations between them. And so I say that there is a relation, the relation Vi, Vj equals something for all I minus j greater than or equal to 2 with the right-hand side consisting of adjacent monomials. Okay, so the assertion here is if I take one of these monomials, if I take any two of these monomials that have appeared here, I take the product of them, then they will fall in exactly one of these cones. And as far as these cones are concerned, these two guys form a basis of the lattice of invariant monomials. They form a basis over Z of the lattice of invariant monomials. And I've got something in there which is a positive combination of them. So it's a positive combination in a unique way, consisting of adjacent monomials. Adjacent monomials means successive points on the Newton boundary. Right? So this is, you know, sort of quite attractive little calculus. So now finally, why? Let me say y is this x equals C2 divided by this 1 over R 1a, an algebraic variety. So because his spec of this ring, C of V naught up to V k divided by ideal of relations, right? So this ring here, this is just the invariant ring Cxy invariant under mu r, right? And so I don't expect all graduate students know what spec is. What this means here is this is a polynomial ring. So I've got C to the power of k plus 1 with coordinates v naught up to vk. Right? I've got some ideal of monomials holding here, and so inside here I've got the variety of I. So this is the variety of defined by I. So that's the definition of spec. So what properties does this have? So in other words, let's put this, let's go back to sort of simple ideas. I take C2 here. I can map him to CK. K plus 1. I'm taking xy here, and I'm mapping them into V0, V1, Vk. Right, so these guys here are just polynomials. These are just monomials in the x's, right? And the image here is certainly, let me write S here. This is V of I. The image in there is certainly contained in the variety of I here. Okay, now I claim that this is the orbit space. Right, in other words, if I've got 2 points in here, if I've got a point xy there and another point x prime y primed, then they map to the same point if and only if they're in the same orbit of the group action, right? So these 2 points map to the same point here if and only if x is epsilon x primed, y is epsilon to the power of a y primed for some epsilon in mu r. Right? And you just have to think about it. The invariant monomials here include x to the power of r and y to the power of r. Right? So if 2 points map to the same thing, then the value of C2 by x to the r, y to the r, this is mu r cross mu r cover. Right. So far I've only used this x to the r and mu to the r, but if I put in x, y to the x to the r minus a y and x, y to the power of whatever it is here, x to y to some power, then I can recover the power of epsilon that has to go here and the power of epsilon that go there. They control each other. So this is an orbit space. In other words, the map here from C2 to S identifies points if and only if they're in the same orbit of the group. And 2, so S has the maximum regular functions. Right? So the polynomial functions on S. S is an affine variety. He's an affine variety because he's the variety of an ideal here. And the regular functions on here are the maximum number of possible invariant functions under C2. That's just by construction, because I took the ring here to be the whole ring of invariant functions. Okay. So that's how to construct this variety as this quotient as an algebraic variety. So I'm going to break in 2 minutes' time, but let me do. Let me sort of suggest. Well, let me first say there is some literature. So if you go to my website, plus surfaces plus cyclic, everything I've said comes from a little paper there called cyclic surface cyclic quotient singularities, and also plus homework. So there are about 10 numerical exercises, 10 or 20 numerical exercises here, which, I mean, you know, you need to do a few numerical examples. So, you know, I mean, let's just have a little go at a numerical example. So, for example, if I can do 1/7 of 1/4, right? And so, you know, write down 7 over 3, 7 over 7 minus 4, because 7 minus 7 over 3 is 322. Write down V0 equals x to the 7th, V1 equals x cubed y, and figure out, find the others and all the relations. Right, and then, you know, similar, you know, 45 over 13, for example. This is 427. Right, so same exercise. So you know, I'm going to make a break in a minute, and you can do this during the break. So I'm giving this as just a kind of little trivial little exercise in calculating, but let me just sort of try and say some of the more serious issues involved here. So there's something. I'm not going to do this very formally, but in the world there is something called Toric geometry. So this is varieties with a monomial structure. So, you know, you've seen this. When I described all this ring here, this ring, I wrote down lots and lots of equations still written up here on the board. And the equations have one thing in common, which they are all of the form one monomial equals another monomial. Right? And so if I take one of these rings of invariance, it has the following property, that this is the affine coordinate ring of some algebraic variety, and it has the property that it has a basis formed of monomials, and the monomials form a semi-group in there. Product of two monomials is another monomial. Right, and there are also varieties with a group action by C star to the power of D, D equals the dimension of V, such that there's an open orbit. Right. So, you know, for example, if you think of P2, P2 looks like this. Here's x, y, z coordinates. I can think of the coordinate ring of P2, the homogeneous coordinate ring, but also the affine coordinate ring of any of the affine pieces, is generated by monomial. And I can think of C star squared acting here. So, you know, lambda 1, lambda 2. This is really inside PGL2 as the diagonal, the maximal commutative subgroup, as a diagonal subgroup. Right? So take diagonal matrices here. The diagonal matrices preserve this picture. They don't preserve it pointwise, but they preserve they take the stratification of P2 by its coordinate hyperplanes and by its coordinate points, and they preserve it. Right? And so monomials form a lattice and the monomials are also, I haven't left myself very much room, have I? They're also they are characters of the torus. Right? Characters of the torus. Right? So I have this thing here, torus, C star to the power of D. Right? I can take homomorphism, the representations, homomorphism of algebraic groups, from this is going to be called big T, like this, hom T to C star, and this is M. Right? So the monomials I've been talking about here, if you multiply x by some, if I multiply, if I go back to the original xy plane, multiply x by lambda 1, y by lambda, then this xy is a character of that action. Right? And so these ideas, you've seen perfectly clearly in all the examples I've done, a variety with a monomial structure. I say a variety with a monomial structure is the same thing as a variety with a group action by this thing, by this big torus, algebraic group, having an open orbit. Right? And then you recover the monomials as this lattice. It's the lattice of characters of the big torus. Right? The reason for making this fuss is because in the next lecture I'm going to want to work not with this lattice, but with the dual lattice. So this is the lattice L, is the lattice hom MZ, dual lattice. Right? And it's the lattice of one-parameter subgroups of T, or you can say it in various representation theoretic ways. But at the moment, this is just another lattice. For the purposes, my purposes now, this is just another lattice isomorphic to Z. Right? And so, you know, I've been working, all of everything I've said so far is sort of really very trivial, very easy stuff and so on, but it's reflecting this subject called Toric Geometry, which is a kind of, computationally speaking, is a kind of very useful device in algebraic geometry.